So I already worked on it last time or after class last time. So I just want to show you this, and I'll save it as a document for you to be able to download. But this is the problem that we were working on, and I think as a first example of something that should have been easy, we probably should have picked an easier problem. Uh, so this one was a little bit trickier because it involved like duplicating. It has, it's one of those repeated roots problem. Um, but in any case, I assigned steps to those to the process of the variation of parameters. And so I wrote this up in steps. I don't know if those steps can be, some of these steps can probably be combined, but as we're learning it, we can just think about it as steps, and then eventually we can think about skipping steps. But let's take a look at the process first, um, just to read things out loud and remind you. These steps will pop up in the problem that we're going to do. It says here, first we find the complementary solution, and the complementary solution is a solution to the homogeneous differential equation. And then you would find the y1 and y2, or if there's more, then there's more. And then after you find those solutions, you find the Wronskian, and that's step 2. Step 3, you find W1 and W2, which is a slightly modified Wronskian to help us use Cramer's rule to solve for the system. And step 4, we divide the W1 by W and the W2 by W, and then we're going to get two new functions, U1 and U2, actually U1 prime and U2 prime. And then from there, we integrate, step 5, we integrate that to get U1 and U2. And then those are going to be not coefficients, because we usually think of coefficients as just numbers or scalars, but these are functions that you're going to multiply y1 and y2 by, and then you're going to put them together to create your particular solution for the non-homogeneous differential equation. So that's step 6. And then piece it together from all the way back in step 1, and then that last step that we do in step 6, we add those together to get the general solution to your non-homogeneous differential equation. So those are the 7 steps. Now, this example that we were doing yesterday, we got stuck with integrating, but everything else was going pretty well. So let's remind ourselves what we were doing. Step 1, we found the fundamental solution. We actually found this from a different problem, but it's easy enough to get the fundamental solution pretty quickly. And so we had repeated roots, and so we have e to the 5x and x times e to the 5x. Those are our two solutions. And then we found the Wronskian of that, which turned out to simplify to e to the 10x. So now we find W1 and W2. And for W1, we replace the first column with 0 and the right-hand side of your original differential equation. So 0 and 30x plus 3 is the first column. We'll keep the second column of your Wronskian for the second column here. And then the determinant turns out to be this thing. And it looks like all the W1 and W2, I guess there's only 2 of them, both of them will have an e to the 5x associated with that. W2 found that to be a little bit easier. And, oh, there was a negative here. I think this was one of the mistakes that I made in class. And so make sure that there's a negative sign here. And I think I got it fixed with after that. There you go. Actually, I would have preferred to use parentheses, but that's fine. And then now, so that's step 3, finding the W1 and W2. And then now you divide by the Wronskian, which is e to the 10x. And then you get something like this. And remember that this is u1 prime, and you want to find u1, so we have to integrate. u2 prime is similar, not quite the same. So that's e to the negative 5x times 30x plus 3. And then now this is when you integrate. And when we integrate, this is where we were last time. We were trying to integrate quickly and doing integration by parts. And so I did this one time, and then I realized that your answer should have been the same answer as we got when we did the easier method. And I was getting things that were not the same, and that's because I found out that I left out this negative sign. So using integration by parts and making sure you have that negative sign there, I got this thing. And then this requires a couple of integration by parts also, actually just one. Yeah, just one set of integration by parts. So now we're going to multiply this by we're going to multiply u1 by y1. And you have to look back at y1. y1 was equal to e to the 5x. So multiply this by e to the 5x, and we get something after simplifying, another place where you can make an easy mistake, algebra or arithmetic mistake. We got this, and then u2 gets multiplied by y2, which in this case it's x times e to the 5x. That's y2. And then simplifying that, you get this. And then so we add them together, and then we eventually get negative 6/5 x plus 3/5. And that was the same particular solution that we got using the other method. Undetermined coefficient was the other method. So in the end, we just add them up, and then that's your solution. So if you look back in your notes, maybe 2 lectures ago, you'd see that this is the same answer that we got. Yes? Oh. All right. Oh, okay. So positive 3x minus 9/5. 9/5? Yeah. So this should be positive, yeah? And our answer back then is positive? Okay. All right. Now we got that right. So those algebra and arithmetic mistakes, adding fractions, for example, be careful. Okay? So, yes? Oh, not negative, right? All right, anything else? So I'll, now that it's all correct, thanks for catching those. I'll post this up so you can walk through the process carefully. So if you have the choice between using undetermined coefficients and variation of parameters, the undetermined coefficients was way easier. Yeah. So the reason why we're going over this particular method is because there's some that we're not going to be able to have a choice with. So let's get to those examples. So I think if we just, let me copy everything and then delete some stuff so that we can have the process down. We'll start our notes for today with that information. forgetting to do this. So step 1, fundamental solution. Step 2, the Wronskian. Oops. Oh yeah, that's good. Step 3, the W1, W2. Step 4, divide by the Wronskian to get U1 and U2 primes. Step 5, integrate. Step 6, multiply by Y1 and Y2. And then you should get your particular solution. And then step 7, general solution. All right, let's find an example to do. Number 1, number 2. Let's ease into this. It's number 1, right? It's supposed to be easy. Number 1 and 2 usually. Yeah, this is number 2. All right, let's go for it. Y double prime plus y is equal to the tangent. So we'll start off finding the solutions to the homogeneous y double prime plus y double prime. Let's call it step 1. Y double prime plus y is equal to 0. M squared plus 1 is equal to 0. M is equal to plus or minus I. So we have imaginary numbers here, which means we need to do the sine and cosine. So which one goes first? It doesn't really matter. I usually tend to like to have the cosine go first and then the sine. But as long as you're consistent with your solutions, then it wouldn't matter. So the coefficient is just going to be 1. It's 1 times I. So I have just sine x and cosine x. That's it. We're done with the first step. Right? Remember back then, this used to be hard. Now we're doing it in like less than a minute. All right. Step 2, we get to the Wronskian. W is equal to, now there's a neat thing about the Wronskian for the sine and cosine. We'll see it in a bit. So it's cosine x, sine x. First row, derivative of cosine is negative sine x. Derivative of sine is positive cosine x. So we have cosine squared x minus negative sine squared x. And the Wronskian is 1. Okay. So that's nice. Step 3, we got a couple of them to figure out. The W1 is going to have the same second column, the sine and the cosine for the second column, but the first column is going to be 0 and tangent. You got the sine and cosine. For some reason, I like to do this kind of next to each other. I don't know if that makes a difference. W2 is a cosine x and a negative sine x, 0 and tangent. And so the first one is going to be a negative, and then it's going to be sine times tangent. Tangent is sine over cosine, so we can't simplify that in that way, but you know, we can we'll see if it'll work out. So sine x, tangent x, and then W2 is going to be cosine x, tangent x. but cosine x, tangent x. Since tangent is sine over cosine, the cosines can cancel. That just becomes a sine. So we want to take advantage of those things that we're simplifying. So that's step 3. Step 4, we want to divide by w. In this case, w is equal to 1, so that makes things easy, maybe, except for the fact that we have to integrate it. All right, what do I need to do? I have like a boundary here that I can't see. So u1 prime is w1 over w, which is just sine x tangent x. And so looking ahead, we're going to have to integrate this, but I think this integral is not going to be that bad. U2 prime is going to be w2 over w, is just sine x. That's easy to integrate. Step 5, we find u1 by integrating sine x tan x. Oh, I forgot the negative again. Thanks. So this is where you have to know your integrals and stuff really well. I think this is a sine squared x over cosine. So if you do a simple u substitution, no. What do you have to do? You have to write the sine as a 1 over, yeah, 1 over cotangent. So we have to get a little creative. And if you run out of creativity, you just go to Wolfram Alpha. But yeah, but you can't use it on tests. So I suggest that you really think about your old integrals and go to the Learning Center and help people out that are stuck in their Calc 2 class. So this is the sine and cosine, or sine and tangent is sine squared x over cosine x, right? And then if we write the sine as 1 minus cosine squared, I think we might be getting somewhere. 1 minus cosine squared x over cosine squared x dx. And cancel the cosine squared, you have a negative integral. Now, say it again. What? Oh. Bummer. Anyway, so this is 1 over cosine, that's secant x. And then a negative and negative is a positive plus the integral of cosine x. So, happen to know the integral of secant off the top of your head? It's natural log of something. So minus the ln secant x plus tan x. So that's the first one. The second one, the integral of cosine, is that positive sign or negative sign? That's always a tricky one. And then we don't do the plus c because the plus c's are just not going to, they'll just merge in with the fundamental solutions anyway. So I think this is good. So is everything right here on the u1 side? All right, the u2 side is just going to be the integral of sine. Negative cosine x, and we're done. So that's step 5. Step 6, we just multiply that back with the u1 or the y1 and the y2. Step 6. Actually, I won't need this separator anymore. So y sub p, that's the particular solution, is going to be u sub 1, y sub 1 plus u sub 2, y sub 2. So u sub 1 we found to be negative ln of secant x tan x plus. I guess that was absolute value sine x. So that's u1. Y1 was cosine, right? Cosine. And then we have negative cosine x is the y, the u1, and the y1 was sine. Sorry, 2. So that's it. You can, if you want, multiply things out to simplify this. It's not. I don't think it's necessary. And I think if you're doing this in the homework situation where you didn't simplify things all the way, I think WebSign is pretty flexible with that. It takes in those answers. Yeah. For step 2, I got y1 here. And then this is y1 prime, y2 prime. So the first row is y1 and y2. The second row are the derivatives of y1 and y2. Step 3, this stays the same. And this is 0. And this function here is the function over here. So the top of the column is always going to be 0. And then the second one is going to be the function. And then so that's what happened here. Now this time this stays the same, and then this is the second column that changed. So whatever, think about that as the column, the w sub something is that's the something that's column is going to change. But the w1 and w2 come from w, and then you just take out the column. Yeah. Uh-huh. Yeah, I divided by, we didn't see anything change here, right? It looks weird, but w was equal to 1, so technically I divided by 1. But this is a special case, of course, of sines and cosines and stuff. Anything aside from that, you'll have to actually divide by something. And sometimes when you divide by some other functions, it'll help. Sometimes. All right. This right here is yp, so we didn't quite get to the final answer yet. I'm looking at this. When you distribute, this is there's a positive sine x cosine x and a negative sine x cosine x. So if you want to take that away, it'll cancel, right? And then this would be, so if you added this, like I said, if you added this in the solution in WebAssign, I think the computer will still take it, because it takes your answer and then sends it to Mathematica and say, hey, is this equivalent? And then it says yes, and so it'll be fine. But if you cancel it out, that would be fine too. Just be careful not to make any algebraic mistakes. And so step 8 or step 7, our last step, the general solution. So the general solution is going to be the original C1 times the Y1 plus C2 times a Y2 plus the solution that we got here, which if we canceled the other stuff out, then we just get a minus. I guess this is a minus. And that's it. Questions? So if you compare this to where we got stuck last time, we got stuck at taking the integral. So we got lucky here. We got nice integrals. A lot of times you'll get some weird integrals where you might have to do integration by parts. But you know, if you have those formulas in your sheet of notes, you'll be okay. Yeah. Oh yeah, the cosine. There you go. Okay. All right. So not so bad, right? Not as scary as it was like last time. Yeah, whatever. It's all hard. See if we can. We haven't done one with initial values in a while. Let's see if we could do one with initial value. That would be 19 through 22. 22? 20? So the thing is, with 20, also, actually, most of these, we could do them with the other method. Undetermined coefficients. Yeah. All right, let's do number 20. Let's do it using this method that we're working with. And this assumes we have an initial set of initial conditions here as well. So let's add that on. Okay. So the initial conditions will come at the very end after we write your general solution and we have the C1 and C2, and we just need to solve for C1 and C2. So let's set that aside, not worry about it. Oh, and we do want to make sure that when we solve for the initial conditions, when we use the initial conditions to solve for C1 and C2, that we're using the very last step as a solution to this differential equation. So I remember seeing that, reading that as a warning, that you don't want to put these initial conditions after the first step, because the first step, it looks like we got the homogeneous differential equation already. But this is not a homogeneous differential equation. So let's go. Let's do this. We'll start off with a homogeneous differential equation. So 2y double prime plus y prime minus y. I'm going to start skipping this step too, because we can just go straight to the m, right? 2m squared plus m minus 1 is equal to 0. Can you factor that? I think this is factorable if you could factor it. But if there's any point where you feel like you can't factor it and you you're afraid of factoring, just use a quadratic formula. But I think this is 2m and m, and I think there's ones here, and one of them's a plus and one of them's a minus. This is the one that's negative, this is the one that's plus, because the 2m has to be positive when you do the outside and inside. And so here we have our solutions. M is equal to positive 1 over 2, and m is equal to negative 1. So we have e to those things, those powers. So I'm gonna, just to be consistent with the way I do things, you don't have to do it this way, but I like the smaller value is y1 and then the larger value is y2. It doesn't. As long as when you do the w1 and the u1, that you're staying with what you put as y1. Yeah, so it doesn't really make a difference. But I'm just going to be consistent. So y1 is equal to e to the negative x, and y2 is e to the 1/2 x. So that's our step one. And the thing that I was talking about with the initial condition is that we can get the solution to the homogeneous differential equation here and say y is equal to c1 times this, c2 times that. And then try, when you solve for this, when you use the initial conditions there, you're solving for this as a homogeneous differential equation, but it's not. So you want to make sure that you use the initial conditions at the very end. All right, step two, this is where the Wronskian starts. W is equal to, these are our functions, e to the negative x, e to the 1/2 x. And so we just get some extra constants here. I get a negative sign, and we got a 1/2 e to the 1/2 x. So when we multiply this, we're going to start off with a 1/2 e to the, now I have 1/2 minus 1, so that's negative 1/2, right? And then a minus becomes a positive, and e to the same power again, e to the negative 1/2 x. So that's going to get us 3/2 e to the negative 1/2 x. So that's W, or the Wronskian. Now let's get W1 and W2. So W1 is going to be 0 and x plus 1 in the first column. The second column will be this e to the 1/2 x and 1/2 e to the 1/2 x. So this is a 0 minus, this is where I always forget my negative sign, e to the 1/2 x times x minus 1. So I'll hold off on multiplying that, because when I divide, I want to look at the e to the negative 1/2 x and e to the x kind of like right next to each other. W2 is e to the negative x, negative e to the negative x, 0, and the g function. Oh, wait a minute. What? I'm looking at the front here, the y. I think I need to divide by 2. We didn't get very far yet, so let's see. At this point, when you find W1 and W2, you want to look at your differential equation in normal form. And so if you have anything in front of the y double prime, you need to get rid of that. And then that's going to change your f function that you're using. So I think when we're looking for W1 and W2. So when we're looking for W1 and W2, the f function is the function in when the differential equation is in normal form, which means the coefficient of the y double prime has to be 1. So we didn't get very far yet, so this is the only thing that we probably need to change. Do this in a different color, kind of highlight this. I don't know what's going on here. Yeah, so it's just going to be 1/2. This is y double prime plus 1/2 y prime minus 1/2 y is equal to 1/2 x minus, or x plus 1. So what happens next to the y prime and y does not really make a difference, but what does make a difference is that your f function that you're going to put in is that function after it's already set to normal form. So this should get a 1/2. So I think the only thing we need here is an extra 1/2. And that would mean that this is also going to be a 1/2. Suppose I should have just written divided by 2. But that was it. Oh, good thing we didn't get very far. Okay. So now let's find the determinant. That's going to be, I'm going to put the 1/2 first, e to the minus x, and then x minus 1 plus 1. Okay? Yes? Yeah, so this thing here gives me a positive, and then there's a negative. So this is a negative, and then negative e to the negative 1/2 x. Yeah, I think it's positive. Right? Yeah. It's what? Yeah, AD minus BC. Yeah. Oh, the derivative's negative. Wait. The derivative, this was negative. Yeah. Okay. Oh, I put a minus. Yeah. All my little mistakes, good practice for you guys to find mistakes on things. Whew. All right, now let's divide by W. U1 prime is going to be W1 divided by W, which is not a nice 1 anymore, but you got a 1/2 e to the 1/2 x, x plus 1 divided by W was this 3/2 e to the negative 1/2 x. So now you got to negotiate in your head what this means, right? You're subtracting powers or something like that. So this is a 1/2 x minus negative 1/2 x. 1/2 x minus negative 1/2 x. So it's just x. Yeah, 1x. The 1/2 divided by 3/2, the halves would cancel, and then it's just 1/3, right? So negative 1/3 e to the positive 1x, and then we got the x plus 1. That's we need to integrate that, but that's not too bad. That's integration by parts, and I think it's just one-time integration by parts. All right, so let's look at the u2 prime, which is w2 divided by w. So 1/2 e to the negative x, x plus 1, divide by 3/2 e to the negative 1/2 x. All right, so I think I still get a 1/3. This time it's positive. Negative x minus negative 1/2 x. It's negative x plus negative heck. It's negative x minus negative 1/2 x. So it's negative x plus 1/2 x, which is negative 1/2 x. Okay. All right. So we got our derivatives. Now we need to integrate to get our original functions. U1 is going to be the integral negative 1/3 e to the x, x plus 1 dx. So integration by parts. Let's put this negative 1/3 out here. So u v u dv v du u v. What? I don't know. I'm trying to do this in my head. Let's not. U equals x plus 1 dv equals e to the x dx du equals 1 v equals e to the x. So uv e to the x, x plus 1 minus v du integral just e to the x, which is just e to the x. That would be, if we multiplied it out, it would cancel, right? With one of the e to the x's. So I just have x e to the x. That's nice. Yeah, there's a negative there. Right? All right, so we'll do the same thing on the other side. It looks like it's a similar integration by parts problem. I'm going to take out the 1/3 this time. E to the negative 1/2 x, x plus 1 dx. So u is going to be x plus 1, du is going to be dx. dv is going to be e to the negative 1/2 x dx. So this is where you need to be a little bit careful with these constants. So when you integrate, you're actually dividing by negative 1/2, right? So we can do the division of negative 1/2 here, but you're just going to multiply by negative 2. All right, so this is going to be a 1/3, and then inside of this integral was uv, so that's a negative 2. E to the negative 1/2 x times x plus 1 minus the integral of v du. So I'm going to take out the negative 2 again. Integral of v du. So that's e to the negative 1/2 x dx. I need to integrate that, which is again negative 2e to the 1/2 x. Man. So the negative is a positive, but then with the integral we'll generate another -2. So that's a -2 e to the -1/2 x. Anything cancel? I don't know if they cancel, but yeah, so they won't necessarily, but they will add. So 1/3. So let's deal with the x first. -2x e to the -1/2 x. And then the things that would add up, that would be -4 e to the -1/2 x. Yeah, I don't know if we could do much with that. So it should be 4, but it would be negative, right? So let's see. Yeah, so right here, right now it's +2, but then when we integrate, another -2 comes out, right? The u substitution, u is equal to the 1/2. It's like this thing. So the -2 comes out of this one. That's how the -2 came out the first time. And then when we do it again, another -2 would come out, right? So now it's -4. Yeah, so that's what happens when you skip steps, which is what I'm doing. I think, oh, this one. Yes. Yes. Whew. All right, let's multiply everything by y1 and y2. So u1, y1 is -1/3 x e to the x. What's y1? Well, that's nice. So e to the x, e to the -x would just be 1. And so we just have -1/3 x. And by the way, if we look ahead a little bit, we should be expecting our yp, because this is a polynomial, we should expect our y sub p to be a polynomial also. Okay? And a constant maybe. All right, so that's the first one. And then the second one, this one was a little bit more difficult. u1, y1 is 1/3 -2x 1/2 x 6e to the -1/2 x. And then we're going to multiply this by e to the +1/2 x. So that would get rid of the e to the x's, right? And so now we just have some coefficients and some x's. So this becomes -2/3 x, and that would cancel with that. And then we have a minus 6 times 1/3 is just 2. Then we add them. It's negative 1/3 x plus negative 2/3 x minus 2, which is negative x, yeah, negative 1x. We probably could have gotten this easier if we did undetermined coefficients. Now we need to do the initial conditions. Yeah. So the general solution is C1 times e to the negative x plus C2 e to the 1/2 x minus 2, right? Now let's take our initial conditions with lots of zeros. That's nice. Oh, we need to take the derivative. We got time. Y prime is equal to negative C1 e to the negative x plus 1/2 C2 e to the 1/2 x minus 1 plus 0. That wasn't bad. All right, now let's put in the values. Y of 0, we'll put 0 in for x. So e to the 0 is 1. We got C1 plus C2. Put 0 in for x. Minus 0 minus 2 is equal to 1. Y prime of 0 is negative C1 plus 1/2 C2 minus 1 is equal to 0. So let's rewrite that into a nice looking system. C1 plus C2 is equal to 3 minus C1 plus 1/2 C2 is equal to positive 1. And I think if we just add this, the C1s would go away. Is there a test? For what? All right, so we reciprocal, so that would be 8/3, right? C2 equals 8/3. Plug that back into one of them. I guess the first one would be nice. C1 is equal to 3 minus 8/3. 1/3? 9, yeah. All right, our general solution. Oh, not our general solution. This is our solution now. Positive 1/3 e to the negative x, positive 8/3 e to the 1/2 x minus x minus 2. All right. Yes. Yeah, because they'll probably give you one where you can't use undetermined coefficients.
Are you gonna tell us?
No. Well, because all you have to do is look for 3 things: a polynomial, exponential, or sine or cosine. If the right-hand side is none of those, then you have to use this. Yeah. Polynomial. undetermined coefficients. So for the undetermined coefficients, they only take polynomials, exponentials, and sine and cosine. Undetermined coefficients. So they only take these things. So if you have a tangent, an ln, a 1 over x, some other combination, a secant or something like that, then or even e to the x times sine x, you can't even use this for if you're multiplying. If you're adding e to the x plus sine x, then you can still use this. Yeah. But if it's multiplied like x times e to the x, then you can't use this anymore. You have to use the other one. So this other one really is more versatile, but you can see how much more difficult it is when we have the other easy ones for special cases, but it's still worth looking at and learning because it's way easier. Stepping stone. There is this one other thing that we do talk about called Green's function that is based on this stuff that'll help you solve for boundary problems, but I'm teetering between going over that or not. All right. Ooh. It's probably not worth starting a new section now. All right, our next one is Cauchy Euler equations, and we'll start our next class with this. Oh, we'll probably start our next class with a quiz first and then this. No, you have to do them. So the quiz will probably be on undetermined coefficients. So is that 4.4? Yeah, which also you need the background for 4.3, that's just solving the homogeneous. So homogeneous, non-homogeneous. Okay. All right, we can be done today.